Yeah.
Okay. Yeah, so I'm just going to briefly go over this. Oh, that's my iPad. I have it. So, hold on. Oops, now you're seeing it really went to sleep. Okay, let's see. Yeah, so with the acids and bases, we're looking at what an acid is. So this will help you out with your lab, right? The acid and base lab. You want to know what an acid is and what a base is. So the easiest way to identify the acid at you guys' level is from this general formula, right? So I know you can hear me and then you can see the screen I'm sharing, right? So with the acid, you have hydrogen and then a nonmetal. That's the general format of the acid formula. Or you have hydrogen, an oxygen, and then the other non-metal. Okay. So when you're looking at a chemical formula, most of the time you identify the formula as an acid or a base based on the components or the elements in that formula. For the most part, at you guys' level, it starts with a hydrogen and it can be any of the nonmetals or hydrogen, oxygen, and then any of the nonmetals. The one that just has the hydrogen and nonmetal, this is called the binary acid. So in 1411, we learned that about the binary acid. And then the one that has the hydrogen, the oxygen, and nonmetal, this is called the oxy acid. Okay, so 1411, we should have learned how to identify the acid. And then when it comes to defining what the acid is, there's three different levels of definition. You have Arrhenius definition, which is what we looked at in 1411. And then you have two new definitions, Bronsted, Lowry, and Lewis. With Arrhenius definition, the simplest way of telling you have an acid is it's a chemical substance that when you dissolve in water produces a hydronium ion. So remember, in both of these structures here, the element we have in common that makes the formula an acid is the hydrogen. So this hydrogen is here, this hydrogen is here. So remember, the, oh, I guess I do have this down here. Let me remove that out of the way. Okay, so the acid has a hydrogen. So this is the bottom line. Acid has a hydrogen ion in the formula, right? That's the bottom line. The acid is either H and a nonmetal or H, O, and a nonmetal. And the nonmetal here can be sulfur. So the nonmetal identity can be sulfur, fluorine, chlorine, iodine. I'm trying to see what other elements they are. What else? Phosphorus, etc. Okay. So you have HCl can give you acid, HF an acid, H2S also an acid. So these are examples of different acids, right? And then for the one that has the oxygen, we have HOCl or written as HClO, HBRO, we have H2SO4. Once again, when we look at these examples given to us of what the acid is, the common element we see each time is H, 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 H. So what happens to this compound when it gets added to water? While I'm here, I'm going to say water is not an acid. So I'm going to include H2O here and say this is not an acid. Yeah, it does have a hydrogen and it does have an oxygen, but one of the definitions that the scientists don't provide for the acid is how the acids affects the pH paper. So we'll get to that. But back to the definition here. Arrhenius said an acid does something unique when it gets in water, right? So any of these acids here, acids lose H plus in water. That's the simplest way to define the acid according to Arrhenius. So this is Arrhenius definition. acids lose H plus in water. And then he also says bases lose OH minus in water. Oops, in water. Okay, I should use the term just water here. But there was something that was written in the definition about hydronium ion. So how do we get to hydronium ion? If you look at this right here, once the H plus is lost in water, what happens to the H plus? To make the hydronium ion, essentially, number one, the acid loses H plus in water. So while in water, the H plus combines with one available water molecule to form H3O plus. So some people just jump to the end and say acids lose H plus or H3O plus in water. Okay. As a student, it took me a while because I'm like, wait, how does something like this that doesn't have oxygen produce something that has oxygen? So it's a whole step. It makes the H plus. The H plus combines with one molecule of water to make H3O plus. In the case of the base, we just defined the acid. In the case of the base formula is MOH, metal hydroxide. So what happens in this case here is when the base gets in water, this bond here breaks. So the OH minus, because the metal is positive, the OH minus is negative. That's how they got together in an ionic bond. When they get in water, this bond breaks and then the OH minus goes off and it gets lost and produced in water. So you know that you have a base because the base has this formula. The format is metal hydroxide. So I'm going to show you examples of bases. Okay, so examples of bases here. Following the format metal hydroxide, the metal can be sodium. So sodium hydroxide is a base, potassium hydroxide is a base, lithium hydroxide is a base, calcium hydroxide is a base. You get the idea, right? So metal hydroxide, these are examples of bases. And so imagine you are interviewing people, right? In this case, you're interviewing 3 groups of scientists and you're asking them the same question. According to you, what do you think an acid is? And this will be Arrhenius's answer. Acids lose hydrogen ion in water. Bases lose hydroxide ion in water. So from here on, what we will do based on Arrhenius, or according to Arrhenius, we tend to either use H plus or H3O plus as the ion, the symbol that represents acid. And then we tend to use OH minus as the ion or the symbol that represents base. Okay? So when you're looking at your lab, you see how this makes sense, that the H plus or H3O plus is the ion, right? Because remember, these are ions, or symbol that represents acids. OH minus are symbols that represents base. So fast forward to the future. Grad school level, junior level, my teacher, instead of writing the word acid, he's using the symbol. And by that level, we all understand. Either he uses this symbol or he uses this symbol, that the word acid is interchangeable with any of these symbols. Or he wants to say base, he uses this symbol instead. It's more like a shorthand, but not really a shorthand because it's not fewer letters. It's just a symbol that represents base, right? So once you recognize that, then it's easier when you're reading the text. H plus, H3O plus for acid, OH minus for base. Okay, now we're continuing with this next group, Bronsted Lowry. These are 2 people who worked together and they came up with their definition. So in their definition, what they're looking at to decide if a chemical is an acid is different from Arrhenius. Arrhenius' definition was a lot simpler, but it was also very restrictive. When it comes to Bronsted-Lowry, with them, it's based on the reactions of the chemical with water. To me, that sounds like the first definition. Let's see what they're saying. An acid is a substance that, when dissolved in water, like we saw up here, will donate its proton, the hydrogen ion. Okay? And then a base is a substance that accepts the proton, hydrogen ion. Oh, okay. So here, we're moving on to this next group. And what they're saying is an acid is any chemical. Oh, I think I added this in the wrong place. An acid, let me add the page here. Okay, right place. So according to Bronsted and Lowry, an acid donates a proton in water. And the proton is another word for hydrogen ion. Okay, so when I'm a student at this point, I'm thinking, why didn't you all just use the same terminology, right? Once we're saying acid, now we're saying proton. It's just because the hydrogen ion essentially at the atomic level, all it has left is the proton, so it's called a proton. It lost the one electron. It doesn't have any neutrons, so it's just called a proton. Okay, so another terminology, proton is the same thing as hydrogen ion. Okay. So according to Bronsted-Lowry, acid donates a proton. Then according to Bronsted-Lowry, a base accepts proton. So what we're seeing here is the chemicals being given human behavior or human attributes. There is generous ones, and then there are ones that I guess need help. So they're accepting the generosity. So in Bronsted-Lowry, the acid donates what it has. So just like we saw before, the acid like HCl, HBr, H2SO4. Since all these have the hydrogen ion, therefore the proton, they're able to donate that hydrogen ion slash proton in water. But then this time the water is not necessarily taking the proton. The one that's accepting the proton this time is the base. Okay, so base is any chemical that can accept the acid. Yeah, the acid ion, which is the proton. Okay, that can accept the proton. So this one gets a little bit more complicated because when you're trying to decide Bronsted-Lowry acid or base, you have to see the whole equation to decide which one is the acid and which one is the base, because you have to see proof of donation. If you can see the acid donating and losing the proton, then you can judge it as the acid. Here you have to see for the base proof of acceptance. So the base is any chemical that has just accepted or that will accept the proton. So you kind of have to see proof of this for you to judge it. And we'll do that later on so you can see how it all plays out. Okay? The second step. Third step or third definition right here, we're looking at Lewis, a whole different scientist. And Lewis in 1411 talks about the electrons. So with Lewis, we're dealing with electrons acceptance. And in this case, with Lewis, what is being exchanged are electron pairs. So you have electrons being given and electrons being received. Okay? So acids are substances that can accept electron pairs, and then bases are substances that can donate electron pairs. So this time with Lewis, the acid is any chemical that can accept electron pairs. So the definition of Lewis for the acid has nothing to do with hydrogen. We're not looking at the formula of the acid and saying, oh, the acid must have hydrogen in it. That requirement is nowhere in the definition. So in this case, to judge an acid, we're not looking for the presence of a hydrogen ion. We're looking for this proof or this ability. Does this chemical have the ability to accept the electron pair? So you will see when we're working on this part here, they'll give you the criteria so you can figure that out. The acid is any chemical that can accept electron pair. And then the base is any chemical that can donate electron pairs. Okay? So you're looking for proof. You're making a judgment, kind of like not really like being a judge, but like being an inspector. You're going to inspect the chemical. Is there proof that that chemical can accept electron pairs? If the proof is there, then the chemical you're looking at is a Lewis acid. If there is proof that the chemical can donate electron pairs, you see the proof there on the chemical structure, then that chemical is a base. Okay, so we're going to be doing all this checking and proofing later on, because you will see in the learning goals that this is one of those things you have to be able to accomplish. And in organic chemistry, they actually apply this. They'll tell you, well, this is a Lewis base. And you're like, wait, what is a Lewis base again? Any chemical that can donate electron pairs. So when they use that terminology very casually, very freely, they expect you to know that the Lewis base can donate electrons. Okay? So I'm not going to go into any more details with that. So remember how I told you guys the chemicals used to identify acidity and basicity? Here we are. So here they're showing you Arrhenius' theory, right? His point of view. If he was to illustrate what's going on, acids produce H plus in aqueous solutions. They gave you the acid example here as HCl. You can see. So when HCl gets in water, that's what the symbol is saying. You take HCl acid, put it in water. That's what this is showing. What happens? The H plus breaks apart, so it ionizes. This is called ionizes. Ionizes because you go from a neutral compound to forming ions, right? And then as it ionizes, H plus breaks apart from Cl minus. Okay, remember of these two, only H plus is the acid molecule. This part here is the acid molecule, or acid ion. That's a proper term, acid ion. Okay, so HCl is an acid because it can produce H plus in water. So is the proof there? Yeah. So remember, even though we call HCl an acid, we only call it an acid because it met the requirement, right? Which is ability to make H plus. Check, we saw it. Therefore, we can say this is truly an acid. It met the prerequisite or the requirement. Okay, what about this part here? Remember I told you base has that format, right? Metal hydroxide. So they tell you here, bases produce hydroxide ions in aqueous solution. Our base selected here is sodium hydroxide, aqueous, meaning it got added to water. What happens here again? Since we see a positive and negative charge, that means ionizes. It ionized. Sodium hydroxide ionized, broke apart, the sodium separated from the hydroxide, right? And so we have sodium ion, hydroxide ion. Now, the sodium ion isn't the ion of base, it's the hydroxide ion. So I'm going to highlight this. This is how we know as we're doing our inspection. This is the base ion. Okay, so do we see the base ion in water? Yes, base ion, base ion, base ion, base ion, base ion. So the chemical that produced the base ion is then judged as a base, right? Because we've seen the proof, the presence of OH ion. Do we care about the sodium? No. The sodium is just the counter ion. the escort, the one that escorted the OH ion, right? The other one. Okay. And then we're told here, now that we know what Arrhenius acids and bases are, remember that we learned this in 1411, neutralization reaction, which essentially says acids and bases react to form salt and water. This is one of those equations you want to memorize. We learned this in 1411. You want to memorize this. It's called neutralization. The format of reaction here is double replacement reaction, double displacement. This is back to 1411, where the acid breaks apart, it ionizes, the base ionizes, they switch partners and they form the product. So I'm going to show you how this works out right here. So we're going back to 1411, okay? So we said the acid combines with the base, and then it forms salt and water. So they usually learn this again in biology, right? So remember, the acid has that fat HX. I'll use, or I say H nonmetal. I'll use a simplified version of this. H and nonmetal. Base has a metal and hydroxide. So you add these here to form salt and water. So remember, these ionize, right? I have no idea what the charges are. So when I ionize these, I get H plus, right? And then the nonmetal, based on this, has a negative charge. And then from here, I get the metal, positive, hydroxide, negative. Remember 1411. In ionic compounds, most of the time, the one that's first is positive, the one that's second is negative, okay? So if that was forgotten, that should be relearned. Positive, negative, positive, negative. When they're forming products, they switch partners. Positive and positive cannot go together. So because they're attracting each other based on opposite charges, so positive and negative can go together, then positive and negative can go together, right? So in this first scenario here, when H goes with OH minus, we get water. So here H goes off with OH minus, and we get water. That's how we get the water when these two combine. And then when the metal and nonmetal combine, I'll show here, metal combines with nonmetal, we get the salt. So this is very generic. So I'm just going to write it like this: metal, non-metal, right? This would be called the salt. So salt, we got water here, we got base, we got acid. So this is what we called double displacement. And then what else is that called? Double displacement. And then, oh, neutralization. I just forgot that term. Okay, neutralization. I just set it up here, right? And I just forgot it. It doesn't take much. Okay. Why is it called neutralization? This is kind of out of context, but later on, we will see how these interact with pH paper. Acid tends to have a low pH. Bases tend to have a high pH. And then the salt and water, based on this, tend to have a neutral pH. So when they say neutralization, they're talking about the products of acids and bases are both neutral, ergo neutralization. So if you need to learn that definition or the label of this reaction in context, that is the context, okay? And we use this a lot in biology. So low pH, high pH, and then neutral products. Okay, so I've pretty much gone through here, and I'm moving on. In this chapter, we spend most of our time, majority of our time will be with Bronsted-Lowry theory or definition of the acid, and we'll spend very, very little time on Lewis acid and base. Why? Because organic chemistry picks up where we left off. In organic chemistry, you talk about Bronsted-Lowry acid and base. You spend more of your time discussing Lewis acid and base. Okay, that gets more complex. So we barely get into it in this chapter. Okay, so remember I told you with Bronsted-Lowry theory, we define an acid when we see the evidence of a transfer. So the acid is only an acid if it's willing to give up its hydrogen ion. Okay, and then the base is only a base if it'll accept it. So we're told here the acid is a proton donor, or H plus giver upper. It has to give it off, right? And the base is defined as the hydrogen ion acceptor. So the base has to take in the hydrogen ion. So I'm going to move over here. They also show you how you can tell something is a base, right? We're told here a base structure must contain an atom with an unshared electron. Other words, lone pairs. So they're saying here base must have lone pairs of electrons because it uses the lone pairs of electrons to attach to the hydrogen ion, right? And so that is important. Whatever is going to take in the hydrogen ion has to have that point of attachment, okay, to take in the hydrogen ion. So here's an example of a Bronsted-Lowry acid-base reaction. So we're going to identify the acid molecule and the base molecule, right? According to the definition. Okay, they told us this is an acid and this is a base. So let me go ahead and see if I can add a page down here so we can see. So we have HA. Of course, they already have the label, acid, and then this is a base, and then they show us the products. So here's the thing. If they give you the reactants only, you cannot tell which is the acid, which is the base. If this is all you have, honestly, your answer will be, I can't tell, because you don't have evidence of who gave hydrogen and who received hydrogen, right? But once the transformation has taken place, HA, the bond here broke, so now A is left with the lone pairs and is negative, and then somehow B magically got a hydrogen ion, and now it's charged. So from here to here, oops, I went too far. From here to here, you can see that this molecule here lost a hydrogen plus. In other words, donated H plus, right? Because now in the product, it doesn't have an H plus anymore. And then what happened to B? This gained, or what we call accepted, H plus, because out of nowhere now it has an H plus. So when you see the big picture, the whole equation, then you can see the transformation / evidence of acid behavior or base behavior according to Bronsted-Lowry. You got to see the hydrogen being donated. You got to see the hydrogen being accepted. Okay, so who or which formula gave up the hydrogen? This one here. Because of that, we define this as Bronsted-Lowry acid. Which formula accepted the base? Sorry, the hydrogen ion, this one here. So this is called Bronsted-Lowry base. So the product here is what they become after they accepted the acid, the hydrogen ion or gave up the hydrogen ion. For that reason, they're called conjugate. They're not the original acid or the original base. They're the resultant, what happened after. Okay? So they get the term conjugate. And the conjugate usually means kind of they go hand in hand, yin and yang, or they're a pair. When the HA loses H, it becomes A minus. So this gets labeled conjugate base. It becomes a base, but a conjugate base. When B gains a hydrogen ion, it becomes a conjugate acid. Okay? So the one thing you want to know here as we're going through this is not only you want to know how to label acid and base, also want to know how to identify what gets formed. Okay? So I want to spend some time on that here. Let me give an actual example. I would say HCl. And then for my base, I will use, let me see. Do I want to use water? Let me use something else. I think they do have an example here before I make up my own. Yeah, they do have examples. So I'm going to use the examples that they have when I get to that. So yeah, we're going to be doing it down the road. So I'm kind of getting ahead of myself. So I'll stick with the slides. We're now defining the conjugate acid-base pair. As I mentioned right now, the conjugate acid and base are a pair. They go hand in hand. So to kind of practice knowing how the conjugate acid and base pair works, they started off with this being a base. So we're assuming NH3 is a base. Okay. How do we know it's a base? Remember, in Bronsted-Lowry, the base has a lone pair. You can't see it here, but technically there's a lone pair on the nitrogen. If you drew the Lewis structure, the NH3 will look like this. N, H, 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 and then you have a lone pair here. So technically there is a lone pair on this that qualifies NH3 to be a base. Okay. The other way you know NH3 is a base is the fact that the NH3 is the one that receives. You see here, it accepts H plus to become NH4. So if you see evidence of accepting H plus, it's not really a bribe, it's just H plus, then the original compound that did the accepting is defined as the base. So we have two ways to tell. One is this is a base because it has lone pairs. The other one is it accepts H plus. Okay. So once this NH3 accepts H plus, so you add H and then positive. Well, what does the H go? This H goes over here. So we end up with N in the middle, H, H, H. Then we get the fourth H going here. But where did this bond come from? Remember 1411? I know I'll keep saying, remember 1411? Because that's a prerequisite for this class. One bond is usually made up by two electrons. So the two electrons that were here are used to make the bond. So there used to be two electrons right here. It used to be like this. Now they are repurposed and used as a bond between the N and the new H. But what about the positive? Because the positive doesn't get neutralized, it remains as a positive out here. And that's how we get NH4 positive. Okay? So this is kind of what's happening here. The H comes in, adds to the pre-existing H's. Then the positive comes in. If there's nothing to neutralize that positive with, it just remains. Okay? So how are these two related? The before chemical and the after chemical. They're called conjugate acid base pair. This is what it was, this is what it became. So this is now called the conjugate acid, what it becomes after gaining H plus. Here we now have another conjugate acid base pair. This time water is being defined as the acid. Now, if you were me and I was me as a student, I'll be like, wait a minute, but didn't you just say water is not an acid? Yes, I did. Were you wrong? Not necessarily. In the definition of Bronsted and Lowry, any chemical that has the ability to give, to donate hydrogen ion is classified as an acid, even the ones you wouldn't have classified as an acid in the previous definition. Now, if you go back to Arrhenius, according to Arrhenius, is water an acid? No, and water is never an acid. But according to Bronsted-Lowry, water is an acid if water is donating the proton. Yeah, as a student, I was like, I want a refund. I'm just kidding. No, I was just like, I would get angry at the scientists, like they're not alive. But I would just be like, I don't like you right now, Bronson Lowry. You're making things difficult. Why can't we just go with Arrhenius, right? But yeah, so all of a sudden with Bronson Lowry, is the requirement being met? Is this chemical donating a proton? Yes. So this chemical, yes, even though it's water, is defined as an acid. So water here is a Bronsted-Lowry acid, right? And when water gives up its hydrogen, what does it become? OH minus. How do we get to OH minus? Once again, we have to go to the Lewis structure, right? So I'll draw this right here. Lewis structure. What is water? H, O, not double bond. Lone pair, H. This is water. So the water molecule is neutral, right? But remember, an H and a positive ion has to be lost. So here, this bond breaks. It breaks completely, but both electrons from the bond go to oxygen. So what we have left when this breaks up is the oxygen is left with hydrogen, and you have dot here, dot here. The oxygen gets both electrons from hydrogen. And because the oxygen has all these electrons here, it ends up being negative. This is our OH minus. H plus ends up on its own. And this H plus is the one that gets donated, right? It goes off. It goes off with the other element or the compound. And so hydrogen becomes, or sorry, water becomes a hydroxide, giving off H plus, right? Remember, H plus and OH make water. So now all we have done is broken up water into H plus and OH minus and donated the H plus. H plus is gone off. It's been donated. What's left behind now for every one water molecule is the OH minus. Once again, this is the original acid. What's left over once the hydrogen is lost is OH minus. Together, they're called the conjugate acid-base pair, the before transformation, the after transformation. Okay? So you then need to be able to identify this in the chemical reaction. So we saw this in part, right? And now we're seeing this as a whole. As I mentioned earlier, it's hard to tell what's the acid, it's hard to tell what's the base if you only look at the left part of the reaction. You have to look at the whole thing to recognize who is performing the base role, who is performing the acid role. So from here to here, you can see transformation. Let's see. This has an extra hydrogen, right? An extra positive charge. So this accepted H plus. Therefore, this is the base. From here to here, you can see lost or donated. That's the proper term for the section. Donated H plus, and therefore this gets called acid. So you cannot have acid and conjugate acid. It's always acid and conjugate base. So the products get named conjugate. The reactants just get the regular name. Okay? So a base will accept a proton and become a conjugate acid. An acid will donate a proton and become a conjugate base. Okay? And that's what we see here. Oh, so for this part here, let's pretend this is not here. So hold on a second. I know we're looking at it. We're looking. Why are we looking? Because the formula is here. I'm going to add a couple that are not here. Give me just a moment. We're making acids of this, right? I don't have any other questions. I just have these ones here right now. Okay, so what I'm going to do here is they want us to make acids out of this. I'm going to add a couple. Okay, so I'm adding a few. So the question here was, write the formula for the conjugate acid of the following. Okay, so these are the chemicals provided. And then they're saying, provide the conjugate acid version. Conjugate acid. So if these were converted into conjugate acid, that means that these are now in the base form. Because remember, this is kind of like a yin and yang. Base goes with conjugate acid. So if you went from base to conjugate acid, that means you have to add H plus to each. You have to add H plus to each of these to get the conjugate acid pair, right? The other part. So in each case here, I'll go through and add H plus. Remember, the H will add to the pre-existing H if there's one. The plus will be neutralized by every negative if there's anything like that. So remember, you're adding, so you add H plus each time, right? That's what I'm doing. Okay, so I'll just say here, add H plus. So I already have an H. I'm adding another H. So I end up with two H's, right? Then I have a negative and the positive that neutralize each other. So this one here will have zero charge. And then I have one oxygen. So this ends up with water as our answer. The H adds to the pre-existing H. The positive is neutralized by the negative. Then the O just adds over here. So we end up with two H's and then one O. Okay. Okay. Now over here, I'm adding another H plus. I have two H's already. It adds to this H. I end up with three H's. Oh, my bad. Is my chair in the way? Am I crowding you? Sorry. Okay, I have two H's. I added H there. Now I have three H's, right? So the H has been dealt with. Then what about the oxygen? I add the oxygen here. Then the positive. Oh, there's no negative here to neutralize it. So the positive remains, right? Then over here, so yeah, the O just adds to here. Then you're pretty much just adding together to produce this. Okay. Now again, I'm adding an H and a plus because all bases take in H plus. So over here, I have an N. The number of N's don't change, but the number of H's change. Now I have an extra, yeah, I have four H's. And then the positive remains because there's nothing to neutralize it. Then we continue. Add H plus. Okay. So the original formula did not have an H, so I put an H here. The number of C's don't change, so C. Number of O's don't change, O, 3. Now the negative. Here I have two negatives, but I'm adding one positive to it. The positive gets neutralized by one of the negatives, so this goes bye-bye, it's gone. But then a negative remains, so this ends up with negative. Okay, so hopefully you saw that. The negative is neutralized by one of the positives, and then they are gone. Okay, then I brought this over here. We have a negative charge, so let's not forget that. Let me add H plus. Let me go in order. Okay, so the H's consolidate, right? So now we have two H's, so H2. Number of C doesn't change. Number of O doesn't change. What about the negative and the positive? We have one negative, you add a positive, they neutralize each other. That's it, so we have zero charge. Over here, H plus, and then let's see. You add this to this, H2 plus H, right? So we end up with H3, okay? And then P doesn't change. O4 doesn't change. But what about the charge? A negative and a positive neutralize each other, so the resulting formula has no charge. And so I just got all my conjugate acids from my given base. If you add H plus to each of these formulas, this is what you get, okay? Then we're going to be doing the opposite. Once again, let's pretend we don't see that. So what I'm going to do for right now is, for today, I'll just end right here. So I'll just say end here. And then we'll continue the next part, okay? So yeah, let's do the opposite now. Let's do the base. So for the base here, I'm going to add to this page. I know I said I was going to give an overview. It's hard for me to give an overview because I'm like, it's hard to go over the superficial stuff and the details are not very clear. Okay, so now I'm trying to get the base from the acid. So what I'm going to do here, I'm going to add some parts. These will be my acid. I'm going to add some to the formula we have here. I'll add this. I'll add this. I'll even add this. The point is for us to learn how to do this, right? And then what do I have here? I have NH3, HCO3, CO3, 2 minus H2PO4. I don't know why we have a duplicate of that. Negative. Okay. So here the question is saying, write the formula for the conjugate base of the following. So this time, if they're saying they want you to get the conjugate base, that only means you started from the acid, because conjugate base are always produced from the acid. They don't come from anything else. So conjugate base has to come from the acid. That means all the formulas on the left are acids. How do we get to the conjugate base? Remember, the acid loses H plus to make conjugate base. So how do we show losing H plus? That means it has to have H first of all to lose it, right? Okay, this is going to be a little bit more delicate than the other one. It loses both the H and the positive charge. So here we have three H's. We have to lose one. So we're left with two H's. That's done. So minus H and the positive charge. So we've lost the H, right? We've lost one H. Oxygen amount doesn't change, but we also have to lose one positive charge. So we lost that. And this is what's left behind. We lost both the H and the positive charge. Next, you have to remove one H and then lose a positive charge. Okay, so this part will be a little bit delicate, but I'll explain that part. Once again, lose one H. So the way we write this one here, we don't write it this way, but I'm going to show it because I'm trying to be consistent with the format. So we went from two H's, we only have one H left. The number of oxygen doesn't change. And then we started off with a neutral compound, right? Neutral compound just means the positives and the negatives even out. We have an even number of positive and negative, right? Or negative and positive. That just means we have an even number. So if one positive got lost, because it had to be taken out right here, right? What do we have left over? This still neutralizes that, but what we have left over is a negative that's not being neutralized. So the hydroxide can be written like this or like this. HO minus or OH minus. Okay? Now we're continuing. The saga continues. Remember, remove one hydrogen, remove one positive charge. Okay. This formula only has one hydrogen left. Remove it. All that's left, oxygen. Oh my goodness. It can survive. The oxygen, the formula as is, already has one negative, right? That's not balanced. And then the rest of the formula has a positive and a negative. It has a bunch of these, as many as needed, a bunch of these. So I'm just now looking at the next level. Well, you have to remove a hydrogen. We did that part. Oops. You have to remove a hydrogen. We already did that part. We are left with the oxygen. And you have to remove the next positive charge. So I'm going to remove this one. What do I have left over when I removed another positive charge? I have two negative charges that are not balanced, so you have to include this. In other words, in making a base, the base becomes more negative. So I want to make this note right here. Bases are more negative. Okay, as I'm doing this, I'm hoping you're seeing the trends. And then acids are more positive. Acids are more positive, right? Yeah. So as you're working on this step by step, I like to do step by step problem because if my brain is having an issue connecting to the concept, it gives me a chance it gives my brain some time to catch up. So when I was a student, I loved working problems that were not assigned. I know you can call me nerd, you can call me whatever you want to call me at this point. It made me do better, but I needed to do the extra practice to connect, right? Sometimes, not all the time. Sometimes I just got it. I'm like, oh, I get this. There are times I'm like, nah, let me do the same kind of question back to back to back, and then I see the connection, right? So where was I? Remove one H and then remove a positive. Again, this one here is neutral, right? Positive and negative match. Okay, where was I? Remove one H, so one has to go from here. N doesn't change. The two H's are left because one H got removed. And then remove a positive charge. Remove one positive charge. What do we have? We have a negative charge that remains unbalanced, so that gets shown. This one doesn't get shown because it's still neutralized by that one, right? Over here, okay, remove one hydrogen, remove a positive charge. Okay, we have one hydrogen present. Remove that one hydrogen. We're left with CO3. We already have one negative charge that has already lost its positive, right? And then we have a positive and a negative. They say remove the next remove the next positive charge. When you remove this, now we have two negative charges, so it becomes two negative. Remember, the base is usually more negative. Okay, here it says remove a hydrogen and a positive. Whoa, wait a minute. There is no hydrogen, so you say impossible. There is no hydrogen. The rule must be met. It says to make a base, to make a conjugate base, wait, sorry, to make a conjugate base, right, you're having the acid lose a hydrogen and a positive charge. This cannot behave as an acid. It doesn't have a hydrogen, right? So it's impossible. What about this one here? This one will lose the hydrogen and the positive charge. So one hydrogen gets lost. We're left with one hydrogen, PO4. The negative ion now becomes -2, right? Because remember, as before, the second positive charge is being lost, so now it becomes -2. Yeah, so hopefully as I've gone through all this, you've seen how this plays out. Now, once you've seen all that, this part I'm about to end up on is saying identify Bronsted-Lowry acid and base and their conjugate in each reaction. Identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. So as we have this here, how do I copy this? Copy this. Did I copy it? Oh, copy. Let me add a page here. Add a page. Oh, there. Add a page. I don't know if the internet is slow. Is this the computer is slow? Okay, right here. So let me see how I can make this big. Make this bigger. There. So as we're looking at this, remember, we are looking at the transformation to tell what's going on, right? So I'm going to start with, I'll highlight what I'm looking at. H2SO4. I mean, I want to think it's an acid, but I can't assume, right? H2SO4 has two hydrogens here. Oops, it only has one. Ah, it went from two hydrogens to one hydrogen, and then it's negative. That means it lost slash donated its proton, right? That means this is the acid. The acid is a donator, okay? And then by virtue of that, you never have acid plus acid. You always have acid plus base or base plus acid. That being the case, this is my Bronsted-Lowry acid. This must be my Bronsted-Lowry base. But let me prove it. Let me see. I think I should write the word here because I don't have a lot of space. My Bronsted-Lowry base. Let me see. H2O goes from two hydrogens to three. Yeah, this is the one that took the hydrogen. Accepted H plus or the proton, right? And therefore it's a base for sure. Okay, what about this last one over here? From HCO3 minus, we went from one hydrogen to two hydrogen. Oh, this one here, accepted I'm saying accepted, I'm writing accept. Accepted proton. Okay? Because it increased, right, in the number. What about from here to here? You went from two hydrogens to one hydrogen. That's the one that gave up the proton. So donated proton, right? So as we can see this here, we can tell which one is acid, which is base. The one that accepts the proton is the base. The one that donates the proton is the acid. So this is the acid. Bl acid, Bl base. Oh, they also want us to label the conjugate, right? If it starts off as a Bl acid, it ends up being a conjugate base. And this one here ends up being a conjugate acid, right? So this one here, and instead of from base, it becomes a conjugate acid. And then this one here, a conjugate base.
Shouldn't that
Okay.
H2CO be 2 negative?
This one here,
H2C, yes.
H2Cu. It accepted the proton, right? H plus. So let me write it out here. I know it's kind of crowded over there. It says HCO3 minus plus H2O. Yeah, excuse the crowd. Does this duplicate arrows? I don't know why the format is messed up. So this is what it looks like, right? So hopefully it's less crowded here. AQ, like that. So this one here is gaining, you're adding H and positive. So the H adds here, but this positive neutralizes that. You're asking about this, right?
Yes. Okay,
So
I
this
see it.
positive here neutralizes that, right? And then this one here becomes negative. As I was saying, when I gave you the little tidbit saying the acid is more positive, because when I learned this at first, the teacher is teaching it, and it takes me a while sometimes to learn new concepts. So when she's talking, I'm still trying to build it in my head, and then I look up on the board, and then she's already moved on. I'm like, sis, slow down, slow down. So what I did to kind of help myself until I really got it was when it's becoming an acid, a conjugate acid is becoming more positive. So this is negative, it's gonna become like more positive. If it's becoming a base, it goes step down, becoming more negative. If it's neutral, it becomes -1. So let's see, a negative will become 0. So it's kind of like going on the number line, right? -2, -0, +1, +2. So depending on where you start, if you're starting off here and forming an acid, it's going to this direction. That's kind of how I saw it in my head until I leaned on the math until I got the chemistry, right? If you're starting here and forming an acid, you're going right. You're forming a neutral compound. If you're starting here and you're forming, so this is an acid, it forms a neutral compound. If you're starting here and you're forming a base, it becomes even more negative. So this would be the base charge in the end, and this is the acid charge in the end, depending on where you're starting. If you're starting here forming an acid, it becomes more positive. If you're starting here forming a base, it becomes more negative. So I was more familiar with the math than I was with the chemistry. Yes, even though I was a chemistry major. But I would lean on the math until I got the chemistry. Now I don't use the math so much, but I use the number line to show me where I was going, right? So depending on where your starting point is or the charge is, if they give you this as your starting point, the formula has a charge of +1 and you're making an acid, your acid will end up with a +2 charge. If you start with a formula +1 making a base, you're going more negative. So acids go in a more positive direction, and then base go in a more negative direction. If that helps, right? Yeah. So when I check this one, it formed a conjugate acid, so it goes from -1 to 0. And then this was neutral, right? Like right here, and it formed a base, so it goes one step back. I know, like I wrote this and I made it so complicated, not complicated, but I made it so messy. But yeah, the number line, we rarely have anything more than -3. So -3, -2, -1, 0, +1, +2, +3, like that. So once again, you're going positive if you're forming an acid like that, and then you're going negative if you're forming a base. And you're only going one step as far as the charges. For every hydrogen, you're going one step, right? So from here, oops, bad. Yeah, from here to here, you went from here essentially to here. And then from here to here, you went from here to there. Okay, if that helps. But yeah, so that's the story of this acid base. You have to see the whole picture to know what is being formed. Now, the good thing about you guys' exam is going to be multiple choice, so all you have to do is pick, right? But you still have to pick the right thing. So, yeah, essentially we've ended here. This is where we're going to end. This is a lot for today, but go ahead and watch the other video so you can see play by play. But organic chemistry is more like this slide right here, talking about acids and stuff like that. The definition, the explanation is a little weird, but yeah. So, yeah, this is what I have for today. And I will stop
Thank you so
here.
much.
You are welcome. Have a nice day. As you're working on stuff, if you have questions, feel free to ask me. Even about lab, even about old labs.
Okay. Yeah, just
Okay.
email that. Can I get that professor's email, and then you can email the other person